Now let's learn how to use pointers to access array elements. Right? We already know how to define arrays. In this example, then an array has been defined as of size 10. It has the numbers 1 through 10 stored in it with an initializer list. Right? It has a pointer named PTRA, pointer A, that's going to point to the start of the array. And what it's going to do is it's going to sum up the array elements. Right? Well, let's go ahead and take a look at the different ways then that we can use, in this case, subscripts with pointers. Well, let's go ahead and then create a program. So our program is to, sum the elements of an array. That's its purpose. And so we know then if we declare some array, pound define, a size was 10, and I made them integers. So here's my array A, and we'll make that a size, and we'll use an initializer list with it. In this case, that is 1, 2, 3. All right, there's 10 elements there, and so let's then create a variable called sum. Initialize it to 0, and now we know that we can say for an I equals 0, I less than a size, plus I. We've done this before to sum arrays. We'd simply say sum equals sum plus a at index I, with our familiar array notation. And we could print it out then if we wanted to, Array sum is %d, and then use our sum variable to print that out. All right. So if we build and run, we get a value of 55 here. Now, if we want to use pointer notation with the array, so pointer, in this particular case, the slide said we're going to use pointer subscripts. All we're going to do is we're going to create a pointer, make it point to A, and then everywhere where we're using the name A, we're going to just change that to pointer A, All right. So we make then, since A is an integer, PTRA, and we're going to make that point to A. So PTRA points to the array, to the start of the array. All right. Now in here, if we do this, it's the same thing then as if we were dereferencing. Well, actually, let's go back. Let's just do this. All we did was substituted PTRA was the name here, PTRA for A. That's all we did. We created this pointer A, we made it point to the start of the array, and all we did was change, instead of A here, PTRA. And if we build and run, we get the same behavior. Right now, I'm sure you're asking yourself, why would I ever do this? It's coming up. After this, we're going to get to how we would use these in functions. The thing is using pointer notation is often faster than using the array index notation. And pointers will be handy for other data structures other than arrays. So that's why we need to learn to work with them. All right, so in this case, now all we did was we substituted that. And that's basically the same thing. So PTRA at index I is the same as if we dereferenced PTRA plus I. Right, doing some of that pointer math. Let's see if we get that same result. All right, so now if I change this to, right, if I dereference, then PTRA plus I, putting the spaces in here for your readability. Right, now, if I compile, cool, no warnings, build and run, we get the same result. All right, so we've seen 3 ways we can do this, right? We can actually then do this A at index I. We can create a pointer to point it to A, and then we can say PTR A at index I. We can use, because the name of an array is a pointer to that location, using a pointer in the same way works, or we can use the indirection operator and use the pointer math. This is what's going on behind the scenes, right? This index notation is saying take I as an offset to this base address of PTRA, right, the same way A at index I did, and access those array elements. Right, so we use then the pointer name with a subscript. Right. Now there's another way we could do this as well too. So let's end this. Right, one more way to do this, since the array name is a pointer here, right, instead of doing this, instead of using this index notation here, I'm going to comment this out, and we're now going to use this notation. So I'm going to create the pointer, right? I'm not going to initially make it point to A. I'll set it up as a null pointer. Right. I'm going to say for PTRA, I'm going to assign then A to PTRA. So I'm going to make A point to PTRA. And as long as pointer A is less than A plus then array size. So A plus array size is doing math. A plus a size is A plus a size times the size of, right, and our integer data type is array, that. And that's just one, that's one address beyond the bounds of our array, right, is, right. So that's our stopping location. And now here, semicolon, all right, plus plus PTRA. Well, I'm just having a devil of a time typing. All right. So now I'm going to get rid of all the subscript notation. And here we're just going to now say that sum equals sum plus, I'm going to use the indirection operator with PTRA. All right. So, this is what we had before that produced a 55. This is what we're changing it to. We still get a sum of 55. Right, now if we walk this, all right, run the cursor. All right, here's our values in A. All right, if we now do, right, next line, right, now PTRA is going to point to the start of my array. Sum is equal 0. The indirection operator with PTRA is the same thing when, since it points to the start of the array, that's A at index 0. So next line, we're going, A at index 0 contains the number 1. We're going to add 1 into our sum. Now we can see sum is equal to 1. Now when we increment our pointer, we point to the next array element, which is array at index 1. When we add to sum, we'll then go get the number stored here, which will be 2. So now our sum is 3. 2 plus 1 was 3. Now we're increment our pointer. Our pointer now points to index location 2. Using the indirection operator with this is going to return the value of 3. Right? So our sum becomes 6. We increment our pointer now. Our pointer now points to index 3, which excuse me, will return the value of 4 here with the indirection operator. Right? And we walk through this. A plus A size is just beyond the boundary of our array, so we don't want to go to that address. That's why we have the less than condition there. Right. So what we just wrote was equivalent to doing this, right? And all of this here was equivalent to doing this. And this, we started off with just good old A at index I. We started off here. I'm going to comment out this other. All right, we started off here with what we're comfortable with. Walking through the array, summing up the array elements. Right. Right. If we use the debugger to walk through this, all right, we can see here sums initialized to 0. Here's our array elements. All right, pointer A is null at this point. We're not even using it. Next line, F7. We're going to add then A at index I. Well, I is a 0. A at index 0 will return the number 1. That's what's stored at A at index 0, the value stored there. Right, we add 1 into sum, we initialize I. Well, A at index I is 1, so A at index 1 returns the value 2 that's stored there. Right, walk through. Right, and you can see we walk through the array incrementing I. So I, with the index notation we've seen, is just an offset, right, from the base address of the array. Similarly, our next step was to go ahead and use the pointer here, right? So we turned this off, and then we wrote this code. And in this case, we had to make sure that pointer A was pointing to A. That's necessary simply because I set it to null up there. And now, right, all we did was we made pointer A point to A. We just changed the A at index I to pointer A at index I. Right? We made that one change. We get the same result. Right? You'll run the cursor. Right? Instead of saying A, we're just using pointer A. Right? And we're walking through the array. The index I is still changing. We're still using the index notation. We're still walking through the array. Right? We can see then our sum is doing the same thing until we've walked all the way through the array. All right, that was our next step. Then we said, okay, let's make another small change. So what we did here was instead of using the square brackets for the array, so I need to make pointer A point to A again. Right, we made pointer A point to A. Instead of using this bracket notation, we used the concept of pointer math. We said pointer A plus I, and then we use the indirection operator then to dereference that, right? It's the same thing as this notation. It's just another way of doing this now, right? Which does lead to confusion at this point because you're studying something new and you're wondering why we do it all these different ways. We're going to go into using arrays and functions, we normally use pointer notation with the arrays. So in some of your homework problems, you'll be required to use pointer notation. Other problems, you'll be free to use the notation you prefer, but we'll have to do some homework with this and get some experience with it so you get comfortable with pointers. As you can see now, we're walking through the array in the same way we did before. We've simply changed our notation for accessing those array elements. And finally then, our last step was to say, okay, if we can do this, now let's just, here in the for loop, let's just make pointer A point to A. Let's not use I at all. Let's not use this offset notation. Let's just use the direct idea of incrementing the pointer by 1 every time through here. Because in this loop, all we were doing was incrementing what? I by 1. So why not just increment the pointer by 1 to do the same pointer math? Right? Our stopping condition then changed. Here, I was less than A size. Well, A plus A size, right, is the same as A plus A size times the size of an int. So it's the same thing, except now we're using pointers, so we have to compare. This is an address. We have to compare this address to this address. This was an int. We compared an int to an int. Here we compare an address to an address. We stop then. A plus A size is just beyond the boundary of our array. That's why our condition is less than here, right? But as we walk through here as well, we get the same results, right? All right, same results there for our sum. Right, just many different ways now of using pointer notation, pointer math, than to walk through an array. And this was used for a long time because we didn't have compiler optimization. And this was a faster way of actually walking through the array. It was faster than some of these other operations, right? So that was used, and then the fact is we're going to use pointers then to pass arrays to functions, and pointer notation for their speed. Right, so that's our end of this section then. The next lecture will be how to use pointers inside functions.